The next one is the magnetic property of the lanthanides. We know that an unpaired electron which is not paired having two type of the motion. The first one is also called as the spin motion and second one is called as the orbital motion. In spin motion, an electron revolve on its axis either anti-clockwise direction, or this electron can revolve on its own axis in clockwise direction. So due to this anti-clockwise or clockwise motions of an electron, or due to the spin motion of this electron, the magnetic moment is produced, and this magnetic moment is represented by mu s, and this mu s can be determined by n into n plus 2 whole under root Bohr magneton. Similarly, the electron can also revolve around the nucleus. This motion of the electron around the nucleus or a metal is called as orbital motion. So due to this orbital motion, the magnetic moment is produced. That magnetic moment is represented by mu L, and the mu L can be determined by L into L plus 1 whole under root Bohr magneton. So overall magnetic moment in a metal complex of unpaired electron is called as the total magnetic moment, or we can say it is the sum of the spin as well as the orbital magnetic moment. It is equal to n into n plus 2 plus L into L plus 1 whole under root Bohr magneton. In case of the lanthanoids, we know that the electronic configurations, the 4f1 to 14, after that the 5d 0 to 1, then 6s2, because the f orbitals lie very deeper, so they do not affected by the ligands. So in case of the lanthanoids, the orbital motions do not quench as it occurs in case of the transition metals. The f orbital exists deeper, so the ligand do not affect them. So in case of the lanthanoid, there is no quenching of orbital motion. So orbital moment is also contributes to the total magnetic moment. Up to the gadolinium plus 3, where the electronic configuration is 4f7, means half filled electronic configuration. This spin magnetic moment and orbital magnetic moments works opposite to each other. That's why there is irregular in the value of the magnetic moments. But after the f7 electronic configuration, or when f orbitals are more than half filled, this spin motions as well as the orbital magnetic moments align with each other, so magnetic moments value increases continuously with increase in the number of electrons in the f orbitals. So we can say the magnetic moment neither increase or decrease nor decrease regularly. It first increase that is from cerium plus 3. See, after cerium plus 3 it will show the praseodymium plus 3. After praseodymium it show the value that is neodymium plus 3. After neodymium the value decrease, that is from samarium plus 3. After samarium plus 3 the value again starts to increase, that is europium plus 3, EU plus 3. After europium plus 3 the value increase continuously, and finally this value become maximum up to the dysprosium plus 3. So we can say the magnetic moment of dysprosium, that is dy plus 3, is maximum for the lanthanoids metal ion. After the dysprosium, the magnetic moment starts to decrease because of the decrease in the number of unpaired electron, and finally the lutetium having number of unpaired electron 0, so its magnetic moment also become 0. So I can say the magnetic moment in case of the lanthanoid is maximum for the dysprosium dy plus 3. The magnetic moment for gadolinium is not maximum, although it having the maximum number of unpaired electrons.